So today I want to, like I said, do some complements. So I want to talk about more about torsion in cohomology, which was discussed in other lecture series by Haluk and I assume also by Aurel. But I want to talk about it in some other cases and just sort of give some complements to what they were discussing. And I also want to talk about, since I missed the problem session because of the network trouble, I want to talk about some problems. So, okay. So first, beginning with the torsion, we'll talk about the conjecture of Bergeron-Venkatesh, which you certainly have heard about, and at least in Haluk's lectures. So we have been looking at the cohomology of gamma with coefficients in certain local systems. Most examples we've been discussing have been with trivial coefficients, but we discussed the general case of this local system attached to a representation of gamma. And I want to talk about torsion in the cohomology. So what I want to do is get an integral structure here. So I want to suppose further that this local system has some integral sublocal system. So you can think about it as you have the representation E, you just choose a lattice in the representation E that's preserved by gamma, and such that when you tensor with C, you get the full thing. And this will give you a local system on the symmetric space, and then we can consider, as long as gamma will preserve that. We consider that as being like some kind of twisted version of integral cohomology. And in fact, if we take trivial coefficients, then we're going to get integral cohomology itself as a special case. And you could also consider doing similar kind of integral structures on homology instead of cohomology. Okay, so one thing that's been known for a long time, going back to computations of Grunewald and others, such as Perplata, a student of Grunewald, we know that sometimes we see in these groups a lot of torsion, and sometimes we don't see so much. And it's actually quite dramatic. I mean, as you've seen in these previous talks, sometimes you see like none, for example, for SL2Z and subgroups there, and sometimes you see enormous torsion with like humongous primes that's showing up as in the torsion subgroup. So Bergeron-Venkatesh proposed a reason for why or when we should expect to see this and sort of why this is happening. And we had this quantity delta of G, which is the efficiency, which we've seen it appear in our discussions as the sort of how long the cuspidal range is, how long the range is where the cuspidal automorphic forms contribute to cohomology. But it's defined in a different way, but in any case, it's an invariant for these groups, and they conjectured that we should see huge amounts of it when this quantity is equal to 1, and otherwise we should not see much. In fact, we should see when delta is 0, we should see none, and then when delta is bigger than 1, we should still see some. We just not going to see it growing exponentially, at least with respect to the volume, co-volume of the lattice. So here's the conjecture that they proposed in their original paper. Suppose you start with a semi-simple group, and suppose that group has Q rank 0. So that means that when you take an arithmetic group and you look at the action on the symmetric space, you're going to get a compact quotient. So I haven't been discussing things like that, but I'm sure they've been discussed in the lecture series that happens when I'm trying to sleep. But in any case, it means that it's very different from the kind of things that we've been talking about. Okay, they're already compact when you mod out by gamma. And suppose you take a decreasing family of congruent subgroups where they're getting finer and finer in the sort of most possible way. The intersection of them has to be trivial. If you look at the intersection over all K, all right? Then they considered this limit, taking the homology, the group homology of one of these subgroups with coefficients in this integral local system, and taking the torsion subgroup of that, Okay, so throw away the free part, just take the torsion subgroup, take the size of that and take the logarithm, and then divide that by the index of these congruent subgroups in the original thing. Consider that ratio and take the limit as k goes to infinity. And what they claim is that this actually has a limit. So first of all, there's no reason you would, I mean, a priori, you would expect this to have any limit at all. It could be going to 0, which of course has a limit, or it could be sort of oscillating or doing all kinds of crazy things. Who knows why it should have a limit? But in any case, they conjectured that it does. And in fact, that limit should be 0, except in this one case where you have the deficiency equal to 1, and where you're considering the degree, it's roughly in the middle of the middle degree, where d is the dimension of the symmetric space. Okay, in that case, the limit should be positive, and it should equal an explicit non-zero constant times the volume of the original thing. So d is the symmetric space attached to this setup. Okay, so there should be one group where you see this sort of giant torsion, so big that, because the volume's getting bigger and bigger as you go up this tower. So it's so big that even after you take the logarithm, you're still going to get a non-trivial limit. So that's what Luke was saying. It's growing exponentially with the volume. Okay, and they're actually able to prove their conjecture in the original paper in some cases. So, but actually, they actually were able to prove using certain assumptions on L, which I don't want to get into, but such L do exist for the examples that they considered. They proved an Euler characteristic version of this. Okay, so you don't look at a single group, you look at the Euler characteristic, and they showed in this case that it does, this Euler characteristic does tend to a limit. Okay, there's a non-zero constant they can explicitly compute. It only depends on G, the group of real points, and the local system times the volume. And then what they were able to do is prove that at least in H0 and then in HD minus 1, you don't get anything interesting. And so from that, they were able to isolate this contribution of the remaining ones, and then see that actually in these low dimensional examples, because they're getting a limit in this Euler characteristic like thing, they're actually getting the exponential growth in the degree that they want. So one of the examples they applied this to was the case of SL2, well, not SL2, okay, of an imaginary quadratic field, but if they take the symmetric space for an imaginary quadratic field, which is hyperbolic 3 space, and then take co-compact subgroups there, okay? So they were able to prove under certain assumptions on L, which can be achieved by various L, that they get this exponential growth. Oh, before I go on, let me just point out, you know, where does this deficiency 1 come from, and where does their conjecture come from? So it's actually that the conjecture is really coming from heuristics from arithmetic geometry, in fact, from algebraic number theory. So Bhargava gave some heuristics on the growth of, or so how many number fields there should be when you fix the degree, and you sort of try to count them. And based on that, some other assumptions, they came up with a heuristic argument about how many Galois representations there should be mod p for various primes p. So how many Galois representations where you're looking at, you know, in the torsion in the cohomology. Now we know that they're, because by results of Schulze, which I don't remember the exact timing, but I don't know if they were available at that time. It certainly was believed to be true based on very many examples. It was believed that the mod p cohomology and homology should correspond to Galois representations. And in this case, where the deficiency is equal to 1, there should be way more Galois representations mod p than come from Galois representations of characteristic 0. So there's too many Galois representations mod p that to account for them from the ones coming from characteristic 0. So therefore, there should be lots of these mod p classes to accommodate them in the homology and the cohomology. So it's really not about some kind of, you might think, well, this must be some kind of geometric result about just these manifolds, or at least why you would think that would be true just for this sort of collection of manifolds. But in some sense it's not. It's really about the fact that there's arithmetic information in these homology groups. And on the arithmetic side, the fact that we know that we are able to predict that there should be a lot of torsion in here. It's kind of remarkable. Okay, so we wanted to investigate their conjecture experimentally for some other settings. So for example, we were interested in looking at cohomology instead of homology. We're interested in looking at cases where the Q rank is bigger than 0, so where there was non-compact quotients. And at the time of this paper, this was, most attention is being focused on the case of co-compact. We wanted to see what happens when you have non-compact examples. We also wanted to consider reductive cases where you have so their conjecture was for semi-simple groups, not for reductive groups, although you wouldn't expect much difference really, because like from the first lecture, the difference is a central torus, essentially, and you're probably not going to get a huge amount of exotic number theory from that, but we still wanted to see what's going on. And we also wanted to see what's happening when we don't know that there are Gauss representations attached to these torsion eigenclasses. So Schulz's result is for number field for F totally real or CM field. So as soon as you get away from there, I still don't know that there's no proof that you have Gauss representations attached to those classes. But of course, we believe it's true from many, many examples, and I assume that it will be proved eventually, but at the moment, we don't know, okay? And we also wanted to check that when delta is bigger than 1, we see different behavior. And all these computations were done with Ovner, Mark, and Don, Ash, McConnell, Yasaki. Okay, so the examples that we looked at some cases with deficiency 1 and cases with deficiency 2. So for deficiency 1, we looked at subgroups, excuse me, of GL and Z with n equals to 3 and 4. So those, if you remember back from the table from a long time ago, those are the only ones where the deficiency is equal to 1. As you keep going up in n, the deficiency grows, and so we shouldn't see this exponential growth in torsion. We also considered this non-real cubic field. So this is not a CM field, not totally real. So we don't know a priori that there are Gauss representations attached to these classes. But like I said, we certainly believe it, but there's no proof of it. And we also looked at the case of imaginary quadratic and over GL2 of that. Now this is something that already there was, lots of computations by Haluk, for example. So this is really complementing that work. It's not really a new case, so to speak, but we wanted to also look at other examples. So for example, cases where the field has class number bigger than 1, for example. But in some sense, it was, this was already extensively studied, so it wasn't sort of a new example in that sense. And for deficiency bigger than 1, so we looked at the next GL and Z, which is GL5Z. Deficiency is equal to 2, and this is really, we wanted to try to get as much data as possible, and so we actually did consider some higher GLNs, but it becomes very difficult to get any kind of convincing data that's like to believe that you're really seeing anything. So in this case, we're not just trying, remember, we're not looking at full level, and the full level cohomology for GL6, that can be done on, thanks to, that could probably be done on a napkin in a French cafe these days, but based on what's going on there. But for us, because we have to look at congruent subgroups, we really can't get very far. And we also looked at GL2 over this CM quartic field, the cyclotomic field of fifth roots of unity, which also has deficiency equal to 2. Okay. So what computations did we do? So, well, all we have at our disposal is this complex coming from either Voronoi theory of perfect forms or from Kocher's generalization of it. So we just took the complex of this that we can get and computed its homology. Okay, in fact, we followed exactly what was done by the setup used by Philippe and Gongol and Soule in their great paper on computing with like large GLNZs from a few years ago. So we just took the cells, so we take the cones that meet the interior of the positive definite cone, they pass to certain cells inside the symmetric space after you mod out by homotheties. And so the ones that live in the interior, and they give you a complex, get the chain complex on that, and the differential is how to compute that is explained really carefully in this paper I just mentioned. So it's very easy to implement, and that's what we did. So the kth homology of this complex is not exactly the cohomology. So in fact, the way the shifting works in the indexing is that h lower k of this complex that we're computing is, should be h d minus k, where d is the dimension of the symmetric space. And with enough assumptions on everything, that's what it is. But in the examples we're looking at, we have to sort of modify sort of what we're looking at. So first of all, we're not exactly computing cohomology, but actually we're computing with trivial coefficients. If we were just to work over C, we would actually be computing cohomology with coefficients in the orientation module tensored with C. Okay, and that's what we're using, for example, GLNZ and so on. So we actually do have a non-trivial coefficient system there. And over Z, what we're computing can't possibly give us even the cohomology with coefficients in the orientation module, because to be able to conclude that we're getting cohomology, we'd have to do Borel-Serre duality, but we can't do Borel-Serre duality over Z if this group has torsion. That's just there's a spectral sequence involved and you can't puzzle through it, I guess. So we can't claim that's what we're getting. Okay, so to deal with that, well, we just decide we're not going to care. So if we resign ourselves just to using the coefficients twisted by the orientation module and say that's just in the great tradition of all people doing computer programming, we loudly proclaim that that is a feature and not a bug. And in fact, it really is, because, I mean, the point is this torsion is coming from something in arithmetic geometry. And if we twist by the orientation module, we still expect that we're going to see that same kind of arithmetic information in the cohomology. So we're not exactly computing the analog of what they're computing for cohomology, but we don't care because we still expect to see the relation with number theory, and we expect to see the torsion. So it would be very surprising if we didn't after all that. And also, if we want to make Borel-Serre duality work, we could pass to a field, but we don't want to exactly do that because we want torsion. So we instead just invert some small set of primes. Okay. In fact, if we invert just the primes that divide the order of some element of gamma, sorry for the typo, that's good enough to make this hold. And then we're computing cohomology. And you might say, well, that's bad because, well, if you're inverting, after all, you're trying to look at torsion in the cohomology. And if you start inverting things, well, that means you're going to be killing some of that. You're going to get rid of it. And maybe if you really are unlucky, you've inverted exactly some prime that you don't want to invert because you've just eliminated any hope of seeing the big torsion that you're looking for. But actually, this is okay because the heuristic really basically says that you shouldn't worry about any small finite set of primes. If you take any finite set of primes and invert it, you're still going to see giant torsion, because we expect this torsion is really coming from like large random big primes sort of showing up in the torsion subgroup and filling it out, not from like small primes with enormous exponents. So like if the reason the Bergeron-Venkatesh conjecture was true is because you have enormous two torsion, like you have 2 to some huge number as you're climbing that tower, then we would be losing that because we're going to have to invert that. But we don't expect that to be the case. It is the case that we do see such things in the cohomology. We do see quite often something like 2 to some huge power. But that can't be what's making the limit work. The limit should be working from giant big things, not from, that occur with sort of small exponents, don't occur with large exponents, not from small things with huge exponents. Okay. All right, so here's some example. I don't want to. I'm just going to do some of the examples to try to get to the last half of the lecture today. So here we're looking at GL3Z. So this is a Q rank 2 example. Symmetric space has dimension 5 in this case. And this limiting value, this C that I'm writing here, this is, if we go back and look at the original slide of the Bergeron-Venkatesh conjecture, this is the limiting value that we expect for the cohomology, for this ratio of the log of the order of the torsion subgroup divided by the index. We expect this value. And we did computations for as many cohomology groups as we could do, but the place where we kind of expect to see something is what we're calling H lower 2, and this would be H upper 3 for cohomology, which is the top of the cuspidal range. And we were able to get pretty far, so we use our favorite subgroup gamma naught of n, which has bottom row 0, 0 star mod n, and we're able to get up to pretty decent sized levels here. So not quite up to 1,000, but over 500. And here's the largest torsion that we found, the largest order torsion subgroup. And the only reason that I'm writing this is not because there's some mystical feature of this number that you're supposed to extract from this, but it's just because it's very rare that I get to write a number like this in anything that I'm doing and say, this number was, we found this number. So it's just fun to write it. That's why I did it. But at least it's pretty convincing that it's big, I think. So there's some giant, yep.
Anything about the primes in that
I
number?
didn't write that down. The primes are big. I don't even know actually. I don't. So in some of these examples, say for the imaginary quadratic ones, we very quickly get to a point where we can't factor these numbers and find the prime divisors. But at least, so I don't know. I don't know. But it's if you would like me to leave it here for a while, so you can copy the number down, you could try. It's certainly I'm sure it's divisible by 2. Just from looking at it. But other than that, it's an open question. So here's and it may be in our paper, I just don't remember. Here's some graphs of these homology groups. So these are cohomology groups showing you the behavior. So this heavy black line in the middle is this predicted number over here, this funny looking special value of the zeta function with these extra coefficients. Whoops, sorry. And so in H upper 2, you can see that it does look like you're not, so it does look like you're not tending to 0, okay? So we can't really go far enough maybe to see that you're really landing on that line, but at least it does seem reasonably convincing that you're getting close to that line. Okay, and you can see that the purple dots, there are no purple dots on the axis. So there is torsion. So at some point there's torsion there. And so we want the limit. We want to have this converge. We really need to get up there. Okay, and then if you look at the other groups, you see that yes, they tend to be collapsing away, and you're not getting anything. But actually you do see sort of different behavior in these two groups. So if you look at H3, so H3 lower 3 corresponds to H upper 2. That is also in the cuspidal range. H upper 4 would correspond to H upper 1, which rationally we know it is trivial, but here we see that there's actually something going on with torsion. You see that you have these bands of number, like in the H upper 4, you see these bands, where in these other ones, you just see these kind of blobs of numbers. And the reason is that in H upper 4, what we're seeing is small primes to large exponents. So like this sort of outer thing that looks kind of like a hyperbola is really coming from 2 to some giant power. That's why you're getting this picture. Whereas over here, you really are seeing sort of random giant blobby primes showing up inside the torsion subgroup. So you don't see this kind of like fine structure somehow. And then in H3, you might think, well, these, and so in the case of well, in the classical case of working over the complex numbers, if you have cuspidal class, it's going to show up both in H upper 3 and H upper 2. And the contribution is going to be essentially the same in both. I mean, like if you compute the Hecke eigenvalues in one, you'll see the same Hecke eigenvalues appearing in the other. So you don't get any new information from that point of view. So you might think, well, the same thing should be happening here for, in this case over where we're working over Z or looking at torsion classes, but it's not. I mean, even though both of these groups, the green one and the purple one, are in the cuspidal range, you don't see the same kind of limiting behavior. You see here for H lower 3, it's going to 0. It's just disappearing. Whereas in H lower 3, which is H upper 2, and H lower 2, which is H upper 3, you see the stuff appearing to tend to a limit. So you do see some kind of qualitatively different behavior, even though both of these groups are in the cuspidal range. I believe you already see that for imaginary quadratic as well. So that kind of phenomenon was observed before. Here we see it for an example of higher Q rank and higher R rank as well. Okay. Let's talk about the cubic field for discriminant -23. Oh, I should say, so this is GL3. We did computations for GL4 and GL5. Those are really not as convincing because we were not able to go high enough in the level to really see this kind of behavior. I mean, I think looking at these three pictures, you would believe that you're seeing something different happening in the three cases. And I would say that on the left one, it does look plausible that there's some kind of limiting value that's being climbed up to. Whereas when you look at the data for SL4, SL5, or GL4, GL5, I mean, you don't see that. We really would have to go much further in our computations with level than we can to try to observe this kind of behavior. And especially for GL5, I mean, we really were not able to get very far with computing with level to see what's going on there. We could probably go a little further if we rewrite programs in a faster language or try to optimize them in various ways, but I don't think we would be able to see this kind of collapsing to 0 that we expect. So, okay, so for this other deficiency 1 case that is not investigated before, so we had this non-real cubic field, discriminant -23, what we discussed earlier. So the symmetric space in this case is, so we have one real place and one complex place. So that's why we get the upper half plane H, and we also get hyperbolic 3 space, H sub 3. And if we were doing SL2, that would be the symmetric space that we get. But because we're doing GL2, we have an extra flat factor R, which accommodates for the unit group, which in the unit group in this case is rank 1. So the index of SL2 inside GL2 is 1. Well, it's infinite index. It's not a finite index, and that factor R is accounting for that. Okay. So here's the constant that we're predicting. So that all of this in this fancy looking number comes from the original BV conjecture, except for this regulator factor. So because their conjecture was for semi-simple groups, and now we have reductive. So how should you change it? Well, it should be something like a volume. And what's like a volume when you have units? Well, that's the regulator. So you would expect the regulator to appear in in this volume computation. So this extra factor of R should the contribution coming from that to the volume part of the conjecture should also include the regulator. And that's what we've written down here. Okay. And so we did computations pretty far. We're looking at gamma naught of n. So this time the bottom is star is 0, comma star mod n, where n is some ideal in this number field. And we were able to get up to norms around 5,500, so about 2,000 levels. And this was, when I say full computations, what I mean is we're able to do more cohomology groups, more Voronoi homology groups than, you know, it gets more difficult sort of the further you get down into the complex. But we were able to go further for what we consider to be the most interesting one. So this one should be the one, the prediction would be this was at the one at the top of the cuspidal range. Okay, and there's a little comment about the regulator.
Paul?
Yep.
This field, is this is this Euclidean or is this a dead continuum?
It's a PID. The class number is 1.
It's Euclidean.
Well, the class number is 1. I don't know if it's Euclidean. I mean, I'm sure someone knows there in the audience, but I personally, I mean, like, sometimes you can have these fields that are just not norm Euclidean, or maybe they're not Euclidean with respect to any kind of variation, but I don't know the intricacies of that. So maybe someone will throw it in the chat. There is something in the chat. That's probably some. I found that I can see the chat if I go up here, but now I can't see the chat. Okay.
We can maybe read it to you.
I thought if I put my mouse, oh, there we go. Let's see. It probably says.
Dan says something from the paper, colon, and then nothing else afterwards.
Okay.
Oh, factorization is in the paper.
Okay, good. Okay, well, maybe someone can tell us if this happens to be a norm Euclidean field. I don't know if it is or isn't, but it is a PID. Okay, so here are the groups that we computed, and again you can see quite different behavior. You see this time, you see those bands again, like in H4, H5. You clearly see them, and there's this limiting value that we're the modification of the BV value. And well, I mean, I think anyone would probably see bands in H2 and H3 because you do have some sort of small primes to big exponents, but they're kind of disappearing. You see that like this first in the green one here, you see this band here. Well, that's going down and obviously disappearing, whereas you're still getting lots of stuff here to cluster around this limiting value, okay? And now here we see two groups. So the cuspidal range, in this case, corresponds to the groups H2, H3, and H4. Okay, so that may seem like a bug because we said this deficiency is supposed to be the length of the cuspidal range. What's happening here is that if we were working with SL2, so the dimension of the symmetric space in the case for SL2 would be, okay, in that case, the cone would be 7-dimensional, so the symmetric space would be 6-dimensional, and the cuspidal range would be, oh yeah, sorry, I'm screwing this up. So if I take, in that case, we would have, I have to go back and look here, just because I can't do basic arithmetic in my head. So in the case for GL2, we have the symmetric space is 2 plus 3 plus 1, so that's 6. For SL2, it would be 5 because we wouldn't have this R sitting here. And the cuspidal range in that case would be going between H upper 2 and H upper 3. So there it would have length, the interval has length 1. But because we have this extra flat factor, which is like giving us like a torus bundle over our locally symmetric space, if you can, we could take congruent subgroups where we actually do get a product, and then you think of using the Kuhneth formula. You're just sort of spreading spreading things out by multiplying by, enlarging by like the cohomology of a circle. So that's why the cuspidal range is now grown by 1. It's really sort of artificially been increased because of this extra circle that's happening, this cohomology coming from this torus bundle, which is in this case a circle bundle. So what that's done is it's taken, the conjecture in the semi-simple case would say that you should have this big torsion showing up in the top cohomological degree. And now because we have this extra circle factor, we should see that same kind of cohomology getting spread out in the top degree and then the next degree down. And that's what we're seeing. So here H upper 2 would be in this GL2 symmetric space would be H upper 4, the top of the cuspidal range. This one would be H upper 3, and we see this giant stuff happening in both of them. Whereas in the bottom of the cuspidal range, which would be H upper 2 or H lower 4, the stuff disappears. So we really are seeing the same kind of behavior. It's been artificially moved around because we have a circle bundle over the symmetric space because we're using reductive instead of just the usual semi-simple symmetric space. So here's a picture of sort of the most interesting group. We went quite a bit further. So here the norms of our ideals are getting above 10,000. Didn't write down exactly how far we went, but we went quite a bit further. And you see that yes, we are getting closer and closer here. Seems pretty convincing. Here's the same set of ideals, but now not ordered by the norm of the conductor or level, but instead ordered by the index. Okay, and we still see the same kind of convergence. So this really would be more like what their ratio is. It's not, things should be ordered not by the norm of the level, but by the index. But really, as long as you're going up this, getting bigger and bigger, in basically any sense, you're going to see this kind of behavior. It's very robust under sort of changing orderings and so forth. And here we see the prime levels. Okay, so the reason we include this is that you can see from this, so these black dots are the prime ideals. The green dots that are lightly there is everything. So in the BV conjecture, you have this tower of subgroups. So each one is contained inside the other. Whereas here, we don't really have towers. We're just computing lots and lots of ideals and listing them and making some obvious measure of size of them go to infinity. And we see that we get convergence. And now if we take primes, we're not getting any, there's no towers possible in this list of congruent subgroups because they're all different prime ideals. But still, we see the same convergence. And that's really because, like something Hecke was talking about, the original conjecture was about towers going up with increasing index, but what's secretly going on here is this Benjamini-Schramm notion of convergence. So if we look at these quotients as Riemannian manifolds, the injectivity radius at any point should be going to infinity. So in sort of every possible way, it's spreading out. So it's a much weaker, a much more flexible notion of convergence than what was in the original conjecture. But this data bears out that even under, families like that, you're still going to see the same behavior. And this was already seen in imaginary quadratic case by Hecke. So, okay, so more recently we did some computations with Herbert Don and John Hecke looking at GL2 of imaginary quadratic with no levels. We just look at the full group and sort of let the discriminant get as big as possible. And Alexander Rom had already done computations like this for SL2. And he already observed the same kind of behavior that we're about to claim here. So we were able to go reasonably far up to discriminant negative 2099. And we looked at, again, the torsion in the Voronoi homology just to see what it looks like. And it gets very big. Okay, it gets, again, just even though now we're using full level, and we don't have any kind of common discrete group where all of these live. We're varying over the imaginary quadratic fields. So they're all different discrete subgroups of the Lie group here, but they're not like congruent subgroups inside some fixed group. So it's sort of a really different way. But because of this sort of flexibility of this Benyamini-Schramm convergence, we would expect to see some kind of limiting behavior. And we do. We see that the torsion appears to be growing exponentially with the square of the discriminant. And the square of the discriminant should, we know the discriminant is proportional. So the volume is proportional to the square root of the absolute value of the discriminant. And so here we have like 4 copies of our imaginary quadratic field in our ring of integers sitting inside. Like, think about it sitting inside 2 by 2 matrices. So the square of the discriminant is kind of what you expect the volume to be like. But we didn't try to figure out any kind of precise conjecture. But here's the picture. And sorry, there's like a big gap on the side, but I didn't have time to like read documentation of GNU plot to figure out how to change it this morning. So, but in any case, there's the plot, and you see it looks very similar to these other ones. There does appear to be some clustering around a limiting value, and when I looked at Rom's paper, I didn't see similar discussion. I think probably because of the same kind of problem we had with SL versus GL, even over the integers. It's just, you don't see the same kind of limiting behavior as quickly for GL versus SL. So we also did computations for SL, and with the same kind of levels, the primes, the torsions subgroups don't grow as quickly, sort of. You don't see it as quickly. So, but in any case, it does appear even here that you have the same kind of limiting behavior. Okay. Okay, now to finish, I'll talk about some problems. So I was looking forward to this problem session with Philippe, but didn't work out yesterday because the network problem. So I'm just going to throw in some problems here. And some of these I've already talked about in another previous lecture. So we'll go through those again just to have them in one place, but then I'll mention some other ones. Okay, so just recall from the reduction theory lecture that we had this generalization of Voronoi theory to a larger setting. It's positivity domain that includes, oh, there's a wrong Q there, sorry. That includes Voronoi's case and also includes Hermitian forms where we could take imaginary quadratic field as giving us our lattice structure, and also GLN over an arbitrary number field. And there's some flexibility in the theory because you can choose, you have a choice of what plays the role of minimal vectors to set C in the boundary of C. So C is the positivity domain. That's like the cone of positive definite quadratic forms in the Voronoi case. Okay, and in the standard application to GLN over the ring of integers of number field, we take this analog, the exact analog of what Voronoi himself did, which is we have these tuples indexed by the places V of the number field, and we take integral vectors coming from the ring of integers of the number field, and we take some kind of rank 1 quadratic form built out of them, or Hermitian form. So the star means if it's a real place, we just take transpose. If it is an imaginary complex or complex place, we take the conjugate transpose. Okay, so that's our set C that we use. And the question was, well, are there other useful choices of Xi? So even over Q, there could be other choices of Xi that make some parts of the computation easier or sort of reveal different phenomena. And I don't never seen anybody looking at such things. So I just want to know, are there other useful choices for what the minimal vectors could be? And I leave useful undefined because maybe they're not so useful depending on what application you want. But if I wanted to say compute for large, very big levels, congruent subgroups, the cohomology, maybe I could take some different C that would make the thing easier. And also there's the definition of Xi, but it would be nice if there's some sort of more explicit characterization of what an admissible set Xi is that would be useful. I mean, there's a definition tells you whether a set is admissible or not, but maybe there's some way, like maybe, for example, something like this set that we're using here is the only example in some sense, but there may be some other ones, I don't know. Another problem that we mentioned before is that the perfect points in his theory are just tuples of matrices over R and C, and they don't usually come from F, even if you start with a number field. They actually just seem to be a priori floating point matrices. But when you actually look a little deeper, you see that they come from the Galois closure. So there should be some way to understand this phenomenon and turn it into something that can make computations better. But so far, I mean, experts have confirmed that they believe this is true, but they, at least the last time I talked to them, as far as I know, it's not proved, and as far as I know, it is not useful in computations yet. The other problem we discussed is that there could be dead ends in the reduction theory, and so a dead end is a maximal face of a perfect cone that lies entirely in the boundary. And that never happens for Voronoi, and that also never happens for hermitian forms for imaginary quadratic. But in general, we don't know whether there are dead ends or not. Of course, we don't believe there are, but we don't know. So it would be nice to prove that. I mean, these are all sort of, and the point is we really don't know that much about what it looks like in this case for a general number field, as far as I can see. It would be nice to know more. So these are just some ideas about trying to know more. The other problem we talked about is that we know how to construct decompositions for GLN over F, but it would be nicer to work with SLN over F if we could. And in this case, SLN is infinite index in GLN in general. So there's really a non-trivial difference between these two cases. So is it possible to use his theory to find decompositions for SLN? You have to get rid of that flat factor, and it would be great to do that. Don't know how to do it. As far as I know, even examples have not been really looked at. So, and finally, the last one that I discussed is that we have a really lack of data for polyhedral complexes coming from this setting. So do more number fields. And we did one -20, -23 cubic field. Do more quartic fields. Do other things. And then also there's these other cones. So there's the Hermitian positive definite matrices over the quaternions, and then there's these 3x3 guys over the octonions in the light cone. I assume that some people have looked at least for full level for the quaternion case, although I don't know. I mean, I assume that I would have found out if I were actually there in person and talking to people. So maybe somebody could tell me if there's work in progress there. I know some people have tried in the past to look at this octonian guy, but it's, at the time it was just too big to be, it was a computational challenge that was not able to be dealt with. Okay, so there are just other examples that could be investigated that have not been investigated. And especially not just looking at the case of full level, but looking at congruent subgroups and looking at interesting arithmetic groups with level acting on these things and trying to understand their cohomology. Okay, I think it would be we've gone so far in our abilities to compute that this would be a sort of a natural direction to push in. And finally, I guess there was not the final thing, but the Satake compactifications for reductive groups. Okay, so that's probably a big project. I think it'd be very interesting, especially people studying compactifications. There are a lot of people doing geometric analysis or Riemannian geometry that are very interested in these kind of compactifications. So the case of GLN over F, there you have at least one example kind of staring at you, and that's whatever's coming from Kocher's theory. So already, even for totally real CM, we don't know what to do. But those cases are probably easier because we have, the Kocher complex is better in that case, in the sense that this discrete set C is going to live in a lattice, so it's just going to be much easier to deal with, and that should be like close to being like what we already know for a semi-simple case, I think. In any case, they give examples, and we want to understand the general theory. So that would be a very large problem, but could be very interesting. Okay, so here's something I didn't mention, excuse me, in the reduction theory lecture. So the split group SLN over Q has Q rank n minus 1. So that has sort of the biggest possible boundary when you try to compactify it. There are other groups with the same symmetric space, but with different Q ranks. There are other forms. So for example, there are co-compact forms. There are groups acting on the symmetric space D where the quotients are compact, okay? So actually I should have written, the locally symmetric space is compact, not co-compact. Gamma is co-compact, the symmetric space is compact. So the case where we've seen the most investigation of this is for Q rank 0. So we've seen, we have, people have looked at reduction theory for co-compact subgroups of SL2R for a long time. There's been a lot of great computational work done recent years by like John Voigt and James Rickers. We heard about that in the Banff meeting. And also for hyperbolic 3 space, so Carrel did his work there. So there's been study, people have looked at Q rank 0. And this, a good example where something new is going to happen is n equals 3. So SL3R. So in that case, there are examples of subgroups where you're going to have Q rank 0, co-compact things. You're going to have Q rank 2. Well, that's SL3Z itself and its subgroups. But you also have something intermediate. You have something of Q rank 1. So how do you do reduction theory for that? So the two extremes, 2 and 0, 2 is Voronoi, okay? So that we understand very well, been understood for a long time. Q rank 0, I believe Mike Lubnowski did some computations that he never published for an example there. So at least there's like proof of concept. And of course we have Aurel and Mike's work and sort of doing reduction theory in general. So, okay, we know how to, in principle, we know how to do it. But it would be nice to be able to have something, sort of computationally feasible where we can actually get our hands on examples. And this Q rank 1, well, that's something that maybe there's some mix of the two approaches. Maybe there's something like Voronoi combined with something like what other people are doing in the co-compact case. I don't know. It hasn't been looked at. But so this particular case, n equals 3, would be very interesting because this is a case of deficiency equal to 1. So we expect that there is some torsion version of Jacquet-Langlands. The first people to present this idea is Frank Caligari and Venkatesh in their great book about this. So we expect some kind of relationship between the torsion appearing in the cohomology of these 3 examples. I mean, there should be relationships, but we don't know how to check them. We certainly can't prove anything, but we can try to check to see what's going on there, what is actually happening. So that would be a really interesting example to look at. Okay, now we had a lecture yesterday about computing with Hecke operators. So there are plenty of problems here. So first of all, in the joint work with Don and Avner and Mark, we've kind of looked at for proof of concept for doing computations with 1 Sharblies in various settings and seeing how we need to modify the computation to make it work. As I said in yesterday's lecture, none of that stuff is proved. It's all just, okay, let's try to do it this way and then it should work. And generally, with some minor tweaks here and there, it works. But we need to push those computations to get more data. We don't have the same kind of data that we have, say, for modular forms over, SL2 of Z. We have tons and tons of data that we've had for a long time. We don't have data for these other automorphic forms for various levels because we don't have the same kind of explicit computations done. So the technology's there. At least in one example of GL2 over a CM quartic field, Andy Jones did some computations there and was able to prove modularity of some elliptic curves over that field using using the data from those computations. So there's still plenty of opportunity for work to be done there. And I think these two sort of good examples to look at are GL2 over non-real cubics and GL3 over imaginary quadratic. Those should be within the range of, you should be able to push those computations much further. Also, we have these enormous torsion classes that we found in GL3Z, GL4Z, and also in GL2 over the non-real cubic. We should compute the Hecke operators on those. They are sort of beyond the range of so what we can do with our own sort of naive implementations and our own our own computation. So even for the GL2 over the non-real cubic, we have lots and lots of data, as you see, and it would be great to compute the Hecke operators on that data, so we can compare with data coming from the co-compact side, which was computed by Arel. So we have data, we have potential to compare, but we don't know that we have actually this kind of Jacquet-Langlands happening there because we can't compute the Hecke eigenvalues in our case. It's just, it's too big. So that's a challenge, so do it. Somebody should do it. And then if you solve this other problem for these Q rank 0 and Q rank 1 groups for forms of SL3 over R, so then compute the Hecke action on that, okay? And then we have lots of data for SL3Z going back to Ash, Grayson, and Green from many years ago, so that could be compared, and especially if you look at the torsion in those cases, you could try to investigate torsion Jacquet-Langlands, okay? And I have just a few minutes left. So the last slide. Well, we've looked at one Charbly's quite a bit, so why not go to two Charbly's? So there was many years ago, I did sort of experiments with two Charbly's to see if just sort of a proof of concept to see that the subdivision process should improve things. And certainly, my tests convinced me that yes, they will, but it's never been applied in the setting of actual cycles coming from the cohomology, of something. So I think that would be, that's sort of the natural next step to look at in this kind of game. And a good example to start with is the next, GL2 over quartic fields. So an ATR field is what's called an almost totally real field. It means that it has exactly one complex place, the rest are real. And so if you take a quartic field, ATR quartic field, you should be able to see the cuspidal cohomology using two Charbly's for GL2. And that is also a deficiency 1 group. Okay, the deficiency of any ATR, GL2 over any ATR field is 1. So there you're going to see gigantic torsion, and you could compute Hecke operators on such things. So actually, for this example, we haven't computed any of these polyhedra. So we haven't observed yet, this could be in the reduction theory part of the problems, we haven't observed that giant torsion yet for such fields, but it should be doable by existing technology. You should be able to do that. So that would be a good thing to look at. The final thing, so just come out of some conversations I've had with speakers from other lecture series in this conference. So the question is, can these complexes that are being used by Jenny and Peter and their co-authors to prove vanishing of various cohomology groups and these stability, proving these stability conjectures of vanishing conjectures, can you use them for Hecke operator computation? So they're essentially computing, they're optimizing some kind of complex to prove the result that they want, that these groups vanish at full level when n, is n goes to infinity. But can we use them to actually profitably? I don't mean profitably in the sense that you will make money. Maybe you will. If you do, please let me know. And my team of attorneys will be in touch with you. But in any case, can it be used? So I should warn you that I've stated that problem without the, I don't want to say consent, but I would say, I'm stating this on my own. I think the other speakers in the other lecture series may say that's no. In fact, they probably have even explicitly told me no. Otherwise, but I don't know. I don't see that the things that I'm seeing in those lectures look very similar to the kinds of things that the proof techniques feel very similar to me, to this kind of reduction that you have to do for Charbly. So I just throw it out there as a problem. Maybe it's not. Maybe it won't work.
I will have a similar problem in my further directions tomorrow.
Okay. Yeah, so you should contact my team of attorneys immediately, or they will contact you. Don't worry. Anyway, it's now 1 hour, so I'll stop.
So is there any question?
Sure. I mean, I feel, I mean, there's been multiple definitions of how Hecke operators work with trivial coefficients, but I don't think I've seen yet how it would work with Steinberg coefficients.
Okay. Well, it's different, but then again, it's not really different. So the geometric problem. So you're really just changing coefficients. So instead of dragging, so like when you write down a cycle, instead of just having a rational linear combination of Charblys, you have coefficients taken in some vector space you drag around. So the actual reduction part, this geometric reduction back to being reduced, has nothing to do with the coefficients. It's independent from that.
So, but how do you use? I mean, in the end, the Charblys, whatever they compute something with Steinberg. So, do you somehow use Borel-Sayre duality to translate your computations back to
cohomology?
To cohomology?
Or yes.
I see. And
yes.
that's Hecke equivariant or something.
Yes.
Okay.
That's right. So the operators act on both sides. So you already do that for modular symbols. And I didn't explicitly say that, but so a modular symbol is like a geodesic. Geometrically, it's a geodesic in the upper half plane. And so, but the cohomology is really modular form. It comes from modular form. So there's a pairing between those two by integration. So they're really dual to each other. So already there, the Hecke action on, I said the Hecke action on the modular symbols is really the classical Hecke operator. Well, strictly speaking, it's dual to it by this pairing. So but you're computing the same, the pairing, this shows you that you're getting, the pairing is non-degenerate, so you're getting the same thing. You're computing the same thing by either you do it on the homology side with the modular symbols, or you do it on the cohomology side with modular forms. So it's similar in this Borel-Sayre duality case. The computations on both sides are the same, even though they're dual.
So if you just last little thing. So very concretely, if you have a modular symbol that's just a n by n matrix, right? You would just take your Hecke the matrix that you have in the Hecke operator, multiply it from the left and multiply the transpose from the right, and get something out that's not.
Yes, but you also, I mean, you have to also have to act on the coefficients.
We'll talk about if it's not that simple.
Well, I mean, it's not just that you act on the modular symbol. The modular symbol is a pair of the matrix giving you the modular symbol together with its coefficients, which is in some module. And so you have to, when you want to compute the Hecke operator, the first step is you multiply by those coset representatives. And you do that on the modular symbol part, just like before, but now there's a non-trivial action on the coefficients. So you have to write down the matrix that does that. So in our joint work with Avner and Mark, Mark computes the cohomology, he's computing the cohomology with twisted coefficients. And then he hands me a list of the resulting cycles together with a list of how the coset representatives of the Hecke operators will act on the coefficients. And that shows up automatically on a computer at UMass, and then a script automatically unpacks that, computes the Hecke operators. And so the first step, which is computing the Hecke images before they're converted back to the original complex, I have to use those matrices that he gives me. Because all of my computations are really done in the symmetric space, not in the locally symmetric space. I'm really working not working mod gamma. He's taking care of all the mod gamma details. And okay. then once I do the reduction, I give it back to him and he can rewrite it in terms of the basis. So there is something non-trivial going on there with the coefficients, but that's not part of the reduction process.
Okay, thank you.
More questions? If not, let's thanks Paul again.
Okay, thank you.